The rest of chapter 12 is going to be discussions of different colligative properties. Now, a colligative property is a property of a solution whose value depends only on the number of solute particles, not on the identity of those solute particles. So the difference in whatever property we're looking at versus the pure substance is going to be related to the attractive forces and solute particles occupying solvent spaces, and not on any direct chemistry happening between solute and solvent. Our first one that we're going to look at is vapor pressure. The vapor pressure of a solvent decreases when a non-volatile solute is added. So if we look at our diagram here, we have our pure solvent in this first beaker, and there's some amount of vapor pressure associated with that solvent. But when we add a solute that is non-volatile, so it doesn't have a vapor pressure associated with it, then we can think about the entropy, the disorder or randomness. And if you have a solute down here, there's going to be more randomness in the liquid than there was before. And so less of the solvent is going to go into the vapor phase. You can see here that our rate of condensation will increase, and our new vapor pressure is going to be lower than the original. So when you add a non-volatile solute to a solvent, the vapor pressure of the solvent decreases. Another way to look at it is if you put two equal volumes of liquid, one that is pure solvent and one that is a solution that has a different solute in it and the same solvent. What's going to happen is the solvent, it will evaporate from the pure, and it's going to go over and condense in the solution. And so you can't see it in this picture. What's going to happen is our volume of our liquid that's pure solvent is going to decrease, and this volume will increase because of that decreased vapor pressure in our solution. We can calculate our new vapor pressure using something called Raoult's law. And what that says is the vapor pressure of a volatile solvent above a solution is equal to its normal vapor pressure, P naught, multiplied by its mole fraction in the solution. And because your mole fraction in a solution is always going to be less than 1, it's a fraction, the vapor pressure of the solvent in solution will always be less than that of the pure solvent. So our vapor pressure of our solvent in solution is the mole fraction of the solvent times the vapor pressure, the normal vapor pressure. So let's work through a problem using that Raoult's law. Calculate the total vapor pressure of a solution made by dissolving 25 grams of glucose in 215 grams of water at 50 degrees Celsius. We have the molar mass of glucose, we have the molar mass of water, and the vapor pressure of water at 50 degrees Celsius. And we know that our vapor pressure of our solution is going to be our vapor pressure of water by itself times the mole fraction of water. So to find our mole fraction, we're going to have to convert both our grams of glucose and our grams of water into moles. So 25.0 grams of C6H12O6 times 1 mole is 180.2 grams, and we have 0.1387 moles of glucose. Then our water, we have 215 grams water. 1 mole of water is 18.02 grams. So we have 11.93 moles of water. Our mole fraction is going to be our 93 moles of water divided by the 11.93 plus our 0.1387. So we get a mole fraction of 0.9885. So we can take our 0.9885. So our pressure of our solution is going to be that 0.9885 times our normal vapor pressure, 92.5 torr. Which gets us a vapor pressure of our solution of 91.4 torr. All right, so we've talked about how the vapor pressure is less. We can also look at the difference in vapor pressure, that vapor pressure lowering. So our change in vapor pressure, delta P, is going to be the vapor pressure of the solvent minus the vapor pressure of the solution. Or another way of looking at it is taking the mass fraction of the solute times the vapor pressure of the pure solvent. That will get you your change in vapor pressure. If the solute itself is volatile, so let's say you're mixing something like ethanol into water, they both have vapor pressures associated with them, we can just find the vapor pressure of each individual component and add them together, just like we've done for other types of pressure. So the solvent will decrease the solute's vapor pressure, and the solute will decrease the solvent's vapor pressure, and so we can find our total vapor pressure by adding the two together. So the mass fraction of the solute times the normal vapor pressure of the solute plus the mass fraction of the solvent, mole fraction of the solvent times the normal vapor pressure of the solvent. So let's work through a problem like that. Calculate the total vapor pressure of an ideal solution made by mixing half a mole of ether with 0.250 mole of ethanol at 20 degrees Celsius. And we have the vapor pressure of ether at 20 degrees is 440 torr. The vapor pressure of ethanol is 44.6 torr. So we know that our vapor pressure total is going to be our vapor pressure of our ether plus our vapor pressure of our ethanol. Our vapor pressure of our ether is going to be our mole fraction of our ether, so 0.500 moles of ether divided by our total 0.50 plus 0.250, so that's going to be 0.750 moles total, times our normal vapor pressure of ether is 440 torr. So we can find our vapor pressure of our ether is 293.3 torr. Our vapor pressure of our ethanol is going to be 0.250, the moles of ethanol, divided by our total moles, times our normal vapor pressure of ethanol is 44.6 torr. So we get a vapor pressure of ethanol of 14.87 torr. So our total vapor pressure is going to be those two numbers added together, which gets us an answer of 308 torr. Now, Raoult's law is for ideal solutions. In reality, there can be either strong or weak interactions between the solute and the solvent, and you can see that if there's strong interactions, as our mole fraction increases, our vapor pressure deviates negatively from the ideal. If there's weak, then we're going to get more vapor pressure than predicted. So just know that Raoult's law works for ideal solutions. Real solutions are going to deviate in one way or the other.